Okay, let's do video 2 of sine waves, some properties of a sine wave. Right. Okay, so properties of a sine wave. What is a sine wave? So a sinusoidal wave shape is used to represent one cycle of an alternating voltage or current. So we did that in the last video. If you want to watch the other one, part 1 of sine waves, you'll understand that bit. And here we go. We're looking at it here now, aren't we? So what we're looking at on here now is a sinusoidal wave which is going from 0 volts up to the peak value on the positive side, down to the peak value on the negative side, and back to 0. Okay, right. And here's some properties that we need to be aware of, and we've done these a couple of times on other videos. Let's quickly annotate some of these now. So peak value, if we remember, was this value here. So it could be the peak on the positive side, or it could be the peak on the negative side there. And the peak to peak value, this one, peak to peak value, was this here, down from this bit all the way to there. So from the difference between the positive peak and the negative peak there, that's the peak to peak. So you'll see that sometimes as PP. And the periodic time, that was this, wasn't it? From the time it takes to go from 0 up to the positive peak, through 0 again to the negative peak, and back to 0. So that difference between the 0 and the 0. So it'd be drawn on like this, wouldn't it? It'd be down here. That would be our periodic time. Okay, and frequency, this bit, frequency is how many times it does that in 1 second. So how many times it goes to the positive peak, negative peak in 1 second. Because remember, this is not a slow motion thing that's happening. Because AC current, like we've spoke about briefly, is going like this, isn't it? All the way, all the time, positive to negative, positive to negative. Okay, and the RMS value, we'll go through that in more detail in the next ones, but the RMS value will be somewhere up here, and it'll be plotted on a graph like this, and it's basically 70.7% of the peak value. So to get that, we'd multiply by 0.707. And then the final one, the average value, will be a little bit lower than that. The average value will be somewhere here. Don't worry, we're going to go through these in detail on here. I'm just quickly reminding you of what these are. And that would be 63.6% of the peak, which is the same as, if we come down here, which is the same as multiplying by 0.636. Don't worry too much about remembering them now. I'm just quickly recapping before we start, just to give you an idea from the last video. Okay. So the horizontal axis, yeah, this bit's important over here. If you're looking over this bit now, it's just flashed up. The horizontal axis is time. So down this side here, yeah, that's the time. And going up this way is the voltage. Okay. So amplitude. The wave shape represents a voltage signal. And a signal can also be represented as a current wave shape, okay? The signal is alternating, that is changing polarity between positive and negative. Remember, we just said this is the voltage on this side, this axis here, and it's going from positive on that side to negative. So the wave shape is going into the positive, down to the negative, yeah? And therefore has a peak-to-peak value of 20 volts, peak-to-peak amplitude of 20 volts, because this side's voltage, isn't it? This axis over here, and the peak value over here is 10 volts. And the peak value over here is 10 volts. How am I seeing that? I'm seeing it here, aren't I? It's saying volts, negative, peak is 10 volts. And in volts, the positive peak is 10 volts on this side. So the peak to peak value here, amplitude, so the amount here, is going to be 20 volts. Let's write that up here. 20 volts, peak to peak amplitude. Okay. The final bit, peak to peak amplitude of 20 volts. Yeah. Okay, so the mean value, just a definition of mean value here. So a mean value of a sinusoidal wave shape refers to its average level. You can see it plotted on the graph there, the mean average. So the line representing the mean value. The area of the curve above the line, so this area, will be equal to the area below the line, this area. Values are taken at a number of points throughout one half cycle. When they say half cycle, they mean this. This is a half cycle here because it's gone into the positive and then it reaches here. So a half cycle, yeah? Half cycle. The mean average level is then found by adding all the values together that we took and then dividing the answer by the number of values. Remember, this is just a definition of what the mean value is. But we need to remember this the quick way. That's why I've been saying this is just a definition. We need to remember this way, which is the mean value of a sine wave is 64% or 0.636% of the peak value. So we've been saying that over and over again, haven't we? So the average is equal to the peak times 0.636. There we go. So the RMS value, you can see it there plotted above the mean average value now. And this is another definition, and then we'll show you the quick way that we're going to use. So the RMS refers to the square root of the mean values all squared. So the root mean square, this means that before all the mean value samples are added together, they are squared. Now don't worry too much, just go with this. The total of the addition of these squared values is divided by the number of samples, and then the square root is taken. But again, here we go. So the RMS value of a pure sinusoidal wave shape is 70.7% of the peak value, which is the same as, like we said here, the same as multiplying by 0.707. So let's write that on here. So equals, the RMS equals peak value times 0.707. That's what we're saying here. And the significance of the RMS value of a sinusoidal wave shape. This is worth remembering this. This could be a quick exam question, this one. So what is the significance of the RMS of a sinusoidal wave shape? And it is that this value produces the same heating effect as an equivalent value of DC voltage. Okay, just bear that in your mind. Let's explain this with a further example now on the next slide here. So RMS value example. We've got a sinusoidal wave shape there on the right hand side. Okay, and it's got a peak value of 10 volts. We know this now, don't we? Because the peak value, we've gone through this now. This is the peak value here, okay? Peak equals 10 volts. Right, we can see that, can't we? Its root mean square value, the RMS value, will be 0.707 multiplied by 10. We've done that, haven't we? So we know now that, because we know that the peak is equal to, the RMS is equal to the peak multiplied by 0.707. We've said that several times now. So the RMS value will be 0.707 times 10, which equals 7.07 volts. So a DC voltage, like we said on the last slide, a DC voltage of 7.07 volts would have the same heating effect in a circuit as 20 volts peak to peak, represented by this alternating current sine wave. So another example. A sinusoidal wave has a value of 650 volts peak to peak. What is the RMS value? Okay, fine. So if we know that the RMS value, that's what we've been asked for, and we know the peak to peak value. So at the moment, if we know peak to peak value, we know this value. Let's draw it. We know this value from here to here. But if you watch the previous video, we know that we need to divide this by 2 because we don't want this. We want the peak value, which is this or this. Okay? So let's rub this out and then we can go on to the next bit and see what the solution is to this one. Okay, get rid of that. Yeah. Okay. So if peak to peak value equals 650 volts peak to peak, we must divide that by 2 in order to obtain the peak value. Like we've just gone through that, haven't we? So peak value equals 650 divided by 2, which is 325 volts peak. You're going to see it as P there. When they're saying PP, they mean peak to peak. P means peak, okay? So the root mean squared, the RMS value, is equal to 325, because we've just worked out, haven't we, that the peak value is 325, because we had the peak to peak value of 650 volts peak to peak. We divided it by 2 to get our peak value, which is that one. And then we know that in order to get the RMS equals peak times 0.707, which is what you're seeing over here now. And that's equal to 230 volts. So in other words, if we look at this, the 230 volts AC mains electrical supply in the UK is actually 650 volts peak to peak. When we refer to the 230 volts AC supply we are quoting, the equivalent DC potential of the supply. So don't panic about that, just be aware of that. And the periodic time. Okay, so we know the periodic time is the time it takes for one complete cycle. Yeah? The horizontal scale is given in time. So this horizontal scale here, this is horizontal this way, isn't it? And this is given in time. Yeah? So the graph reveals the periodic time of the wave shape. And it shows that one complete cycle takes 8 milliseconds. So you're thinking, how have I got 8 milliseconds? Well, look, one cycle is from going to 0 to the peak, down to the negative peak, and then back to 0 again. So the periodic time for this one is there. Just in there like that. Okay, let's draw our arrow there. So we're measuring, that's why they've measured up to here. They've drawn this arrow in already, one cycle. And each one of these, 1 millisecond per division. When they say that, they mean that's 1 millisecond there, 1 millisecond, 1 millisecond. So they've counted them up. 1, 2, 3, 4, 5, 6, 7, 8 milliseconds. Right. So the periodic time for this signal is 8 milliseconds. Fine. Okay, so frequency is measured in hertz. I mentioned this previously on the other video. And the frequency of a signal refers to the number of times per second the signal completes a complete cycle. So let's draw it over here again, just so we get a visual idea of what it means. So that's one cycle, yeah? One cycle. So frequency, yeah, is how many times it does that in 1 second. Right, okay. So for example, a signal which completes 1,000 cycles in 1 second is going to be how much? It's going to be having a frequency of 1,000 hertz or 1 kilohertz. So if the periodic time of a signal is known, its frequency can be measured using the following equation. Frequency equals 1 divided by the time. The time is equal to the periodic time. Look over there. So T is equal to the periodic time. Like we counted on that last one when we counted the millisecond increments, the division was 1 millisecond each little square. Okay. So, yeah, here's the same graph again. So we had it, didn't we? So each one of these was 1 millisecond. So we know that this full cycle here, this goes from there to there. Yeah? So this line was 1, 2, 3, 4, 5, 6, 7, 8. So 8 milliseconds. Let's look what we get now. So periodic time equals 8 milliseconds. Notice there how I've not gone through that, but obviously we need to convert down to our base value, don't we? Milliseconds is not the base value. Seconds is the base value of time, isn't it? So 8 milliseconds is equal to 0.008 seconds. Practice that if you can't do that. So the frequency is equal to 1 divided by the time. So 1 divided by 0.008 is equal to 125 hertz. So that's the frequency of this particular signal that we're looking at. So quick summary of sine waves then. Okay. So we understand straight away, don't we? When we look at this, the axis on this side is for voltage, positive or negative. Remember the positive side's here and the negative side's here because AC is going positive, negative, positive, negative, positive, negative. And you're seeing one cycle there. So a sine wave is a sinusoidal wave shape is used to represent one cycle of an alternating voltage or current. And the key properties of a sine wave are peak value, peak to peak value, periodic time, frequency, RMS, and average. We've gone through them at the beginning and throughout these two videos, so go back through them. So the peak to peak value is the amplitude of the wave. So in volts from peak of positive to the peak of the negative. So from the peak of the positive to the peak of the negative. That's our peak to peak value from there to there. Half of this to get the peak value, remember? So we do the PP, which is the peak to peak value, divide by 2, and that's going to give us our peak value, which is this value. Okay. And there, peak value is half of the peak to peak value. Peak equals half, peak of 1/2 cycle, positive or negative. Okay. The frequency is the amount of cycles per second. Remember, this is one cycle there, from 0 back to 0 again. Once it's gone positive, negative, and back to 0, that's one cycle. And it can be calculated by that, can't it? Frequency equals 1 divided by time. And remember, if we need it the opposite way around, and we've got the frequency, we need the time, that's equal to, time is equal to 1 over the frequency. Okay, so there we go. Periodic time, the time to complete one cycle, that's what the periodic time is. So across the bottom here will be our periodic time on this particular one. It'd be starting here, yeah? And it'd be going all the way to when it goes back to 0 on this side over here. Okay, the RMS was the peak multiplied by 0.707 because it's 70.7% of the peak value. And the average was similar, but it was slightly lower. So it was the peak value multiplied by 0.636 because it's 63.6% of the peak. So I suggest you watch that video and the other video again, and you go through it and you go onto the worksheet and try out the questions, okay?